Yes. After 1, so we have already started filming. Hello everyone. Okay, we're going to start. Welcome to MathSoc. Listen to me, please. This is Linda Frey. She is from Switzerland. So welcome to Linda. Thank you so much for coming. I just want to tell you all, just before we start, we are filming this lecture. So if you ask a question, you will probably be recorded. If you're from the back, maybe speak up. And if you're in this, like I think these front 2 rows, they can see the back of your head, or in the front here, they can see us. Hello. So welcome. There's popcorn. Enjoy. Ask questions if you are okay with that. That's up to her. And yes, let's go. Thank you so much for coming.
Hi. I will just close this door. That's okay. So hello everyone. I'm very glad to see that many people are here. And many people seem to be interested in elliptic curves and why they're beautiful and why they're useful and what we can do with math in actual real life. So I'm Linda, I'm a PhD student in Switzerland with Philipp Habecker. I actually work with elliptic curve in my research, but I do not do the things that I will present here. These things are just for showing you the beauty and the usefulness of the elliptic curve. So the first question is, what is an elliptic curve? So I will give you a definition. So we take 2 integers, a and b. They have to fulfill a technical condition, but we should not worry about this. This is just to make sure that everything is correct. And then we will look at coordinates in the plane. So these are just points, x and y, with rational entries, so x and y are just rational numbers, and they have to fulfill this equation. Okay, well this looks like something from school. We know that, we can just draw that. And it looks like this. Okay, actually this should be symmetrical to the x-axis, which is not quite the case, but it should be. Okay, these are just the points in that set. So these are just x and y. So we have x here and y here that fulfill this equation of y squared is equal to x cubed plus ax plus b. So now we also need to add another technicality, which, well, the first years should not pay attention to this, but if you maybe are in a second or third year of your studies, then you could keep in mind that we add another point to this set of points, which is at infinity. So it is infinitely far away from this point, just somewhere around here. It doesn't even fit on this blackboard. Okay, what is the cool thing about elliptic curves? Well, why should we take elliptic curves? Why can't we just take any equation here and do something with it? What is the cool thing? So, well, the cool thing is we can add points on the curve. So how does this work? I saw that you have colors here, so I'm going to try that out. So let's say we have here a point P. Does this work out, or should I take white?
It might not work on the video, so maybe take yellow.
Yellow is a good idea. So this is a point P. This is a point Q. And now we can add those points just by drawing a line through them. And now there's a little bit of math magic here, because there's always exactly 1/3 point of intersection here. which is it's a big theorem, so we just believe it. And since our curve is symmetrical to the x-axis, we can just reflect the point by the x-axis and always get exactly 1 point here. And this will just be the sum of our 2 points here. So we just define this. This is the sum of P and Q. Okay, what else can we do? We can add a point to itself. So we take another third point. We take this one. I have to think about which point I take because this picture should not be too complicated in the end. So I take this point. And again, we take a line through that point and through that point. So it's just a tangent line on the curve in this point. So let's try to.
Nice.
Okay, and again we have exactly 1/3 point of intersection here, and we've reflected on the x-axis here, and this is our point 2 times r. Okay, what? So, yeah?
Is this defining the addition and, I don't know, 2-time multiplication operators? Or is this just how it happens? Is this the definition?
This is the definition, yeah. So this is, I would say this is, well, the definition that makes the most sense. Also, I could not imagine how we can define another addition that has the nice properties of this one, because it has some properties, which I will tell you now. So, the addition on this curve, let's call it just plus, together with this set of points, and well, together with this point, is an abelian group. So, some of you may not know what an abelian group is. It's not a problem. So, abelian group just means that we have this addition here, and it has the nice properties that we want from addition. So, it is commutative. It doesn't matter if we add P plus Q or Q plus P, because the line through P and Q is the same as the line through Q and P. We have an inverse, so if we have any point on the curve, we can find another point, which is the reflection on the x-axis, and then add those 2 points. Then we will get the neutral element, which is this one. So you should not think of it if you're just maybe in first year. And another nice thing, which is, but it is also a bit complicated to show, is that the addition is also associative. So if you take P, Q, and R, 3 points, then P plus Q and then plus R is the same as Q plus R and then plus P. Okay, but this is just something on the side to show you elliptic curves are really good because of this property, because they are an abelian group, and the addition, it is nice because you can explain it to anyone. You can explain it to your grandmother or your mother. Hi, Mom. So, now the next thing, the amazing thing that I find about elliptic curves is they are part of Diophantine theory, Diophantine equations, and Diophantine equations have been studied since 2,000 years, and elliptic curves themselves have been studied for, I think, 150 or 200 years, and they are used in everyday life. So in all of your lives, they're probably used every day. And that's what I'm going to explain next. So I will give a short introduction to modular arithmetic.
Oh, it might be easier to move the bottom one up and then the other one down.
That makes it easier.
Some of them are smoother than others.
Or maybe I should So modular arithmetic. It sounds crazy and complicated, but it's not that hard. We take the clock. So it's 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So if it's 11 a.m. and something takes 2 hours, this is actually like 13, but we say 1 p.m. So on the clock we just forget about multiples of 12 that we add to the hours. So 1 is the same as 13. 6 is the same as 18. And if something would take 12 more hours, it would also be the same as 30. So we can do the same thing with other numbers. So for the next example, we will take a clock with 5 hours. And on this clock, if we have 4 and add 2, which is 6, then this would again be the same as 1. So we have 4 and add 2 and get to the 1, even though 4 plus 2 is actually 6. But in this clock arithmetic, it's the same as 1. So now we will look at elliptic curves, where the coordinates here are no more rational numbers. There are hours in our 5-hour clock. So there are integers in z mod 5z. And I will take this one. And that's what we do with cryptography. We take elliptic curves over finite fields. So here our finite field is F5, which is just the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So just the hours on our 5 hours clock. And we want to look at an elliptic curve, so I will give you a concrete example, and we will take points and add them. So the curve will be y squared is equal to x cubed plus x plus 1. And then yeah. So if someone asks an uncomfortable question, then I will just okay, so we have this elliptic curve, and now the set of points with coordinates in F5 will just be all x and y, where x and y are in F5, such that y squared is equal to x cubed plus x plus 1. And just by using how we calculate things in those in this 5 modular arithmetic, we can compute that these are exactly the points 0, 1, 0, 4, 2, 1, 2, 4, 3, 1, 3, 4, 4, 2, 4, 3, and this crazy point at infinity. So we actually have points that we can look at, and they're made of actual numbers. We can almost touch them. That's how real they are. And I will try to make a picture that's similar to that one up there, and then we can try adding points. It's not a good idea giving a talk on white blackboard and with lectures. Okay. So we have our coordinate system. And we have 1, 2, 3, 4. 1, 2, 3, 4. And now we just write the points here. So we have the first point is 0, 1. We call them names. So let's A, B, C, D, E, F, G, H. So this is A. Then we have 0, 4, which is B. 2, 1, which is C. 2, 4, which is D. 3, 1, E. 3, 4, F. 4, 2, G. And 4, 3, H. I hope I draw everything correctly, and I hope my next drawing will work out. So, the thing is now we want to add points here. Let's just take 2 points and add them. Let's see which ones are a good idea. Okay, we will add C and H. So we draw a line through them. Damn it, there is no third intersection point. So what happened? Why isn't there a third intersection point? I said there's always a third intersection point. The thing is, I only draw the points in here. But on the clock, with the 5 hours, I just erase it here. For example, this point is the same as 3, 1. But it's also the same as -2, 1. So here's E again. And everything just repeats itself everywhere. So, for example, this point B, which is 0, 4, it's also 0, -1. So it's also here. And we have a third intersection point, and we can mirror it on the x-axis, and we see that C plus H is equal to A. Okay, so we made it. We added points on an elliptic curve over a finite field. It sounds very crazy. And that's what we do in cryptography. So for cryptography, yeah?
Shouldn't it be B?
No, because we draw the line, get the third intersection point, and then reflect it on the x-axis. Yeah?
How would addition with an element with itself be defined in this?
Yeah, well, this would be a little more complicated because you would actually have to compute the tangent, and so you would have to do some ugly computations. And it's, well, from the picture here, you can see what the tangent would look like, but from the picture here, you cannot see it. So you would have to do some computations. And this would be far too complicated for you.
I don't yet see the resemblance between the top board and the bottom board.
So here we just...
I see they both have the same definitions of addition, at least.
Yeah, so we have much fewer points here than here,
Yeah.
because we just have much fewer points or much fewer numbers available to put in here for x and y. So where we have the rationals, we have infinitely many points, different points that we can try out. So we have x can be a rational number from -infinity to +infinity, and excluding infinity, and y can also have infinitely many values. So we just get a kind of smooth curve. But here we have only 5 possibilities for x, 5 possibilities for y. So there can be at most 25 points on the curve, and not all fulfill this equation, so it will be much less than 25, and there would just be those points. If we would write those points in here, so let's just write this. D is also here, F is also here, and H is also here. Then it looks a little bit more like this one above, because, yeah, well, it's kind of like something here. You see maybe the similarity between those, and they both have this symmetry on the x-axis.
They both have elliptic shapes.
Yeah, but the word elliptic, it doesn't come from the shape. It comes from the origin of this equation, because that comes from integrals that want to compute the length of an arc of an ellipse. But yeah, it misleads the people, because if you're a mathematician and telling people that you work with elliptic curves, then the people say, oh yes, I also did that in school, I know what an elliptic curve is, and they just write this. And then you have to say, no, it's slightly different. Yeah. Okay, where was I? Yes, what do you need for cryptography? I think I will erase this one. So, what we need in cryptography, when we, well, in cryptography, we have the possibility of always having a stranger trying to read what we send out. So we cannot put a person on a horse and say, okay, write to my friend there and give them the key so we can encrypt things. You have to communicate through a public channel, for example, the internet. So the goal would be having public material and private material and doing some stuff, and in the end, both people have something that no one else knows, and they can use this for encrypting something. And the main ingredient for this, most of the time, is a function that goes from somewhere to somewhere, that's easy to calculate, but the other way around, so knowing the result and trying to guess or compute where it came from is hard. That's what we call a trapdoor function, because you can go in the one direction but you cannot go back. And one trapdoor function that was used for a very long time was multiplying two primes. Because if you have two large primes and you multiply them, then for a third person who doesn't know those primes, it's very hard to calculate what those primes were in the beginning. So the RSA procedure used the fact that multiplying primes is a trapdoor function. But it has a very large key sizes, so you have to have a kind of big processor that you can compute your encryption, your key, and with those smartphones and embedded systems and higher needs for security, we just need better things. So we just need things that have the same level of security but smaller key sizes. And that's where elliptic curves come in. So elliptic curves give you a trapdoor function with this property, so one direction is easy, the other direction is hard, and you don't need a large key size. I will tell you how that works, and why we need those finite fields for it.
Sorry?
Yeah?
Can you give an example of the sizes we were talking about here?
Yes, I will give it after, in the end. Okay, so we have in cryptography, the people that talk to each other are almost all the time Alice and Bob.
They're very chatty, those two.
Yes, and the person that's always very evil is Eve. She wants to know what they're talking about. Maybe she's in love with Bob or something like that. So, or Alice, yeah. So they both have a a natural number. Let's call them NA and NB. Let's write here, okay, what Eve knows is the public information. So we have an elliptic curve. We have a point on that elliptic curve. And we have the order of the point, which is just the number of times you have to add it to itself until it becomes this crazy point at infinity. Okay, so Eve knows all this public information, and Alice and Bob only have their numbers, and they are small or equal to n. Okay, what do they do? So they both multiply, add this point to itself the number of times that their number is. So Alice computes NA times P, and Bob computes NB times P. They exchange their values through public channels. So Eve knows what NA times P is, and she knows what NB times P is. So Alice got from Bob this point with coordinates, so just a pair of rational, or not rational numbers, a pair of integers. And she takes that point times NA. So she takes that point and adds it NA times to itself. And Bob does the same with Alice's point. Okay, so what do they have? They both have a point, NA times NB times P, and Bob has NB times NA times P, but this is the same point. So they have an information that Eve doesn't have. Could Eve now compute what this point is? No, she couldn't. She only has NA times P and NB times P, but since multiplying a point with a number is very easy, but finding out this number, if you only have the point, and so she knows P, and she knows NA times P, and from there to there it's easy, but she cannot compute this NA just by having P and NA times P. So Eve cannot find out what these points are.
Can't you just divide by P?
No, that's the point of this being hard. So you have a point, say it's 5.5, or let's say it's 4,3 in this elliptic curve, and you know that the point in the beginning was 0,1, and you know that this is just NA times this point. And so it's very hard to compute what NA is. Yeah? So you do the line thing NA times. Question there? Question there?
I just was going to check.
Okay, you said the order of P is being the amount of times you have to add it to itself to get to the infinite point.
Yeah.
Will that always happen? Won't there sometimes be some loops?
This will always happen if we're in a finite field, because there are only finitely many points.
But in an infinite field it won't.
In an infinite field, I will talk about it later for a very short amount of time. Probably. Yeah. Okay, so we have this crypto key exchange, and now I wanted to tell you how large are the key sizes. Let me just think where I got that. Ah, yeah. So we have this elliptic curve cryptography, key exchange, and we have RSA. And if we have elliptic curve cryptography with a 256-bit key size, then we would need an RSA key of bit size of 3072. And
For the same security.
for the same security, yes. And what the NSA considers top secret, so for the documents that they really don't want anyone to read, this would be 384 bits in elliptic curves and 7,680 bits with RSA. And still, the direction from left to right is very easy to compute with the elliptic curves. So you just have the same amount of work getting that key for the same key size, but you would need a really, really big key to get the same security. Okay. So that was the part of the usefulness of the elliptic curves. And it is really the case in most browsers they use elliptic curves. In many applications they use elliptic curve. One problem about them is that some algorithms on elliptic curves are patented, so you cannot use them, and you need to find a good elliptic curve and a good point on it. So there are the NSA, for example, releases or released elliptic curves that you could use. But I think when a few years ago, when Snowden put all those documents online, there were hints that said, well, at least one of those elliptic curves that the NSA gave out to the public has some backholes that only or there might be backholes that only the NSA knows and can maybe use to decrypt things. So maybe they can go from B to A in a more easier way than other people would without this knowledge. Yeah?
Is it possible to prove that a particular point is a good one?
There are some properties that it should have, and then it's a good one, but I'm not sure which properties there are. Yeah. Yeah, we have an expert here, so.
The NSA thing, you're talking about the random number generator actually.
I'm not sure. I just read that on several articles.
So, if we're thinking about the same thing, what happened was that there's a random number generator that uses it's supposed to be a secure pseudo random number generator. It's based on elliptic curves. So you have these 2 points P and Q on the elliptic curve, and then you look at sequences of these points, and then you extract bits from, say, the x coordinate of these points, and they should look like random. But this is called the ECDSA. Sorry, it's not ECDSA. It's dual EC random number generator. But it turned out there's a trapdoor in it. And the funny thing is, you give it to any elliptic curve person, they go like, yeah, there's a trapdoor in it. But the standards body that was looking at these random number generators didn't have number theory people on it. So it just had symmetric cryptography. So if you look in the standard documents going back and forth, it's Don Kelsey, who's he's a really good block cipher guy, but that's symmetric cryptography. You've got his marginal notes saying, guys, I'm out of my depth. I don't know whether this is true or not. I don't know anything about elliptic curves. You're checking this, right? And his friends who are on the standards body who work for the NSA were like, it's fine. Clearly, I really hope that John told me that himself. So that's why now with the NSA ciphers and lightweight block ciphers, they've just given the world called Simon and respect. The whole world's going, thanks a lot, but actually no thanks.
So that's a good answer to the question, why should we train mathematicians? Because we really need them. So the last part of my talk will give you a small insight of what I almost actually really work with, namely heights. And in a way, I will try to give you an intuition on how they are used in proofs. Namely, I will give you a very short insight into the proof of the Model theorem. Okay, so what are heights? Heights are a way to measure the arithmetic complexity of a number. So what is the definition? So we take a rational number here. X and y are integers. They are co-prime. That just means they don't have a common factor. And if they would have one, so we could just cross that out. And we define the height of x over y just by the logarithm of the maximum of the absolute value of the two. So let me give you a few examples. What's the height of 1 over 10? It is the log of the max of the absolute value of 1 and 10. So absolute value of 1 is 1, absolute value of 10 is 10, the maximum of both is 10, so it's the logarithm of 10. What is the height of 10? It is the logarithm of the maximum of the absolute value of 10 and 1. Because 10, we could also write it as 10 over 1. Oh, which is the same as before, it's log 10. So although the numbers are not the same at all, they have the same height. And the other direction can happen as well. So we can have two numbers that are almost the same, but they have really different height. So let's see what the height of 0.99 and so on is. Well, this is just 99999 over 100,000. Yeah. So it's the logarithm of the maximum of this number and this number. And this number is bigger, so it's the logarithm of 100,000. So this number is almost 1. What's the height of 1? So it's again the logarithm of the maximum of 1 and 1. So it's the logarithm of 1, which is 0.
So all your logs base 10.
It doesn't matter. So for me, there are the natural logarithms, but it would only change by a factor. So it doesn't really make a difference. So if this is now 5 or another number, it would just differ by a constant. So, but the values for the heights are extremely different. So the numbers here are almost the same, but in kind of arithmetic sense, this is much more complicated because it has so many digits, and this one is just not complicated because it's just 1. Okay. There are again some nice properties for the height. No. First, we can also define a height on our elliptic curve. So if we have a point on an elliptic curve over Q as here before, so the coordinates are just in Q. We have P as X and Y. Then we can define the kind of naive height of this point just as the height of the X coordinate. And now we have nice properties of the height. So one nice property that we have is if we take a set of rational numbers or a set of points on the curve, and we only want to look at the set of points, in that set with bounded height, so they cannot have a height more than the constant that we want to pick, then these sets are finite. So first property, sets of bounded heights are finite. The next property is probably also one reason why this elliptic curve cryptography is so much better, is the height of 2 times p is more than 4 times the height of p minus some constant that only depends on e. What does that mean? So that actually means that if you add a point to itself, the complexity of the x-coordinate will increase. So the more times you add a point to itself, the more complicated the x-coordinate gets. So maybe also the more complicated it gets to go back, go in the other direction. And yeah, I'll also write that one. If you take one point fixed, p0, and add any other point to it, then you have this inequality with some constant here depending on the curve and this point. So you take some point p0, and then you know if you add another point to it, the height of the point that you get will be at most twice the height of the point that you add to the point and some constant. The thing is, in most proofs and in most applications, those constants, they are not a big problem. So the important thing is always the kind of intuition you get by taking this inequality. So, now a very famous theorem about elliptic curves is due to Mordell and maybe also Dale. It says that. Is there a question?
Well, if you take that second equation and make p not equal p, then you've got the height of 2p on the left, but it's got to be less than 2 of the height of p plus a constant, but it's got to be bigger than 4 the height of p minus another constant. Is that going to be okay because of the constants?
Either that, or maybe you're also not allowed to take p0 here.
Okay.
Yeah, I'm not sure at the moment. Maybe you can answer. You have an idea.
I think you've got to take p0 fixed and let p vary along.
Yeah, p0 is fixed, but then p can become p0.
No, but it needs to be on a separate line. That's the kind of thing.
But it's not allowed to be p.
Ah, okay, so it's not allowed to be p. Yeah.
Well, it is, but then the constants work out in a certain way, right? I mean, the constant, the second constant here is allowed to depend on p0. So that if p is specifically p0, then the height is actually relatively small. But for many other, or
Yeah, of course, you can just look at this equality. Well, this is true for maybe all but finitely many p, and this just makes up for those finitely many because you just take this as the maximum of the arrow term that occurs with those finitely p that you don't want to look at. Yeah, maybe that's a good question. Okay, so I'm going to tell you now Mordell's theorem. I think it was 1922. So rather old for research math, but maybe rather new for math in general. we have an elliptic curve defined over Q. So just as in our definition, this A and B are integers. And then the theorem says this E of Q is finitely generated. So what does this mean? Finitely generated just means that we can take a finite set of points, and then every point that is in here can be expressed by a linear combination of those finitely many points. And now I want to try to answer your question from before. So this then looks like something like this. And some, let's say like this. So we have some part of the curve which is kind of like this modular arithmetic from before. So where every point, if you add it to itself, it will become the 0 point. And there are other points that you can add to themselves that will just go somewhere. So you can add them infinitely many times and you will not reach 0. Yeah. That's just as a short excourse.
So in particular, this is interesting that a set of rational points is actually infinite. Otherwise, if it's an infinite, I mean, every finite set would be finite.
Yeah, so if we would have no copy here of Z, then the curve would in itself be already finite, and then it would not be interesting, but I think in about 50% of cases, there will be something here.
Questions don't know what linear combinations are. So
okay.
Questions means that you'll always be able to pick a finite number of points. So these are special points that we picked, and then we can get every other point by adding multiples of these points. So adding these ones we picked, adding them to themselves some number of times, and then to each other.
So that's in math terms what it means. We have a point on this curve, and this point is sometimes some number times 1 point there plus with every point in there.
And the big X are the generators.
Exactly. Those are finitely many, and those are exactly those finitely many generators. Okay. So I will just very quickly give you an intuition on how you can use the height and what you need of the properties of the height. Well, my timer said that I'm already at 45 minutes, but I think it will take maybe 3 more minutes. Another property of the height, now it gets complicated, not a property of the height, a property of the curve, is that this is finite. What is this now? Okay, it's just as before, we had the hours on the clock, but now we're not looking at hours and can add 5 hours or 10 hours. Now we're on the curve and can add any duplicate of any point, and it will stay the same in this kind of setup. So we just take it for granted that this is finite, and so we take any point on the elliptic curve, and we want to show that we can find a finite set of points on the curve such that we can represent this point as a linear combination of those points. So since this is finite, we can just look at this point in this set. So this finite set, we call the things in here Q1 until I don't know, let's say Qn. So there will be a point Q1, which is equivalent to this P in this setting. So it will just differ by a duplicate of any of some point, so some point that we find. And we do the same thing for this point. This is a point on the curve. We can look at it in here, and let's say I1, and we get another Q and another P, and so on. Let's say we do that m times, and yeah, okay, like this. So we do that m times until a certain point that we would have to compute, because of the properties of the height, namely the properties 2 and 3, we can show that at some point for a fixed bound that we fix from the beginning, that this will get smaller than this bound. So there is a point m, there's a step m, where we get below a certain bound regarding the heights of this point, of the height of this point here. So let's say we're at this step, and the height of Pm is lower than a fixed bound. Then we can use the property 1 and know sets of bounded height are finite. And this Pm can only come from a finite set of points that only depends on the bound that we have. So let's say Pm comes from the finite set R1 until Rl. And we can use these equations by going backwards and just putting Pm minus 1 here, Pm minus 2 here, and so on. P1, we put it here, and we get P, which was our arbitrary point, is Qi1 plus 2 times Qi2 plus 2 squared Qi3, and so on until 2 to the n minus 1 Qim plus 2 to the m Pm. But Pm also was from a finite set. So we have a linear combination that represents P, and the things in here only come from those two sets. But those are finite, so the union of it is also finite. And we proved our theorem, finitely generated. Okay. So the second thing was actually the thing about the beauty, for those who didn't recognize that. And I hope overall I gave you an enjoyable insight into elliptic curves and how we use them, and how we use them in real life, how we use them in math. And if you have questions, you're kindly invited to ask me. I think I'm here for maybe an hour. And thank you for your attention.
Now that you've got that for the cryptography, you've got that NA and the key unique point that both parties know. How does that lead to encryption?
You would need another encryption system. So this is only the key that you exchange, and then you would need to encrypt it using that key.
Any other way, okay.
Yeah.
Alright, thank you so much for coming, everyone. I found that really interesting. Like, I've learned a lot in the past hour, and that's always a great feeling. So thank you so much for coming. I hope you enjoyed the popcorn. We do have some shirts on sale. Let's give a big round of applause to say thank you again, because we don't have it. We have some popcorn as a thank you. Yeah, and we'll also maybe let you know if you want to re-watch the lecture video. It's going to be on the social media. So yes, enjoy your weekend. See you next week. Bye. Thank you so much.